Okay, so before we begin, anybody have any questions? All right. Okay, so most of what's been done has been, although Matt did do some basic panel things that try to deal with potential endogeneity in a very specific way. We're going to try to deal with endogeneity at least a couple of different ways today. I'm not quite sure how long this will take, so we'll find out. So first up is matching, which is what they refer to as confounding on observables. All right, so basically what matching is super glorified regression. So let's then begin with a brief attempt at a schedule that may or may not hold true. So I'm going to talk about basically some problems with OLS, talk about a couple of methods to deal with it, including matching, and then some of those as well. I won't do that much on control functions, although I guess I could if we had time. So here's the sort of standard point that we always make in econometrics. And that standard point is quite simple. If what you don't know, the error, right? And let's oversimplify, what you don't know is everything, right? Unless you're Donald J. Trump, right? Who does know everything. Just ask him. So if what you don't know happens to be correlated with something that's in your regression, and in particular, it's the thing you care about, right? If it's correlated with something else, it's probably not such a big deal. But if it's correlated with the thing you care about, then you're likely to get biased estimates. So if we don't have, exogeneity is the uncorrelated idea. Endogeneity is the fact that it is correlated. And what that then means is that the ordinary least squares estimate is equal to the true estimate plus some additional components. And those additional component, well, that additional component in a binary case is fairly easy to talk about. In a multiple regression setting, it's not quite as easy to talk about because there's a lot of other things going on in the background. So the covariance between X and U, right? So this is the component here. Basically, how correlated is it? The more correlated it is, the more bias you're going to get. Okay. And then that is tempered at least somewhat by the variance in X. So if X has very large variance, the bias then would drop a little bit as well. And it's fairly easy to sign, right? So you know whether you have upward bias or downward bias based on your ability to know what the sign of this covariance is, or what the sign of the correlation is, right? So if X and U are positively correlated, what we typically talk of as positive selection, then the actual estimate you get is the true estimate plus some things, right? So it's overestimated. On the other hand, if you get negative selection, you get the correlation between X and U is negative, then this term is negative, and so your actual estimate is the true estimate minus some stuff. So it's actually underestimated. Okay. The other thing to keep in mind is when we run a model, doesn't matter what model we run, we're guessing, right? We are trying to fit reality. Actually, this is even funnier. We are trying to fit a line over reality, right? It's a pretty hard thing to believe is true, right? The world isn't flat. It's hard to imagine why we should be able to think flat, okay? I don't know how much time Matt spent on the conditional expectation function and some of these kinds of things, but there is a reason to think that a flat regression is a reasonable approximation if all you care about is what's going on at the mean. If you care about beyond the mean, then assuming essentially that the world is flat is not the greatest of ideas. Okay. So we're going to set this in a very specific framework. Again, I think Matt talked about this at least briefly, but I'm going to bring it up again. The framework we're going to use is something called a Rubin causal framework. And sometimes it's Rubin and someone else, and I forget the someone else at the moment. So my apologies to that person, since they deserve some credit too. All right. So we're going to imagine this simplistic story where we have two types of individuals, or maybe two types of countries, or two types of states, or two types of firms. All right. So we don't. I'm using agent here as loosely as possible. The only point is that it's micro in the sense that I can look at a particular entity. So there's some sort of treatment. If you're a macro type person, you might be interested in the effect of inflation targeting, right? So you could think of inflation targeting as a treatment. If you're a micro person, you might think about the impact of having access to medical aid on health status, or you might be interested in the effect of completing matric on job opportunities, or some things along those lines, right? So treatment is also meant to be fairly generic, right? What kind of thing might happen to you, or might a policy be put in place to make something happen to you, right? And we call that a treatment. Obviously, the wording comes from health, right? Because you go to a doctor, the doctor treats you. Okay, that's where it comes from. But we don't need these to be health interventions whatsoever. Okay, so an agent either gets a treatment or does not. And then the causal framework then is essentially tying the outcomes to the treatment status. So DI is equal to 1 for treatment, and then I define Y1 as the outcome for the treated. Okay, so this is a notation issue. DI is 0 means they don't get treatment, and then Y0 is the treatment or the non-treatment outcome. Okay, so this is some notation. I don't care about any sort of regression at this stage. I'm just sort of thinking out loud. So there are two types of population measures we could imagine. One is a generalized average. What is the expected difference in the treatment outcome net of the non-treatment outcome? Okay, so that is what we call the average treatment effect. It is the overall average in the population between the treated and the untreated. There's actually two, but we typically focus only on the first one. We can also think about a conditional average treatment effect. You can condition it either on who was treated or who was not treated. So I'm just going to use the treated component for now, right? It's a subpopulation measure or a conditional population measure, right? So the tau is the standard Greek letter that gets used for this, and we're interested in the expected outcome of the treated given treatment relative to the expected outcome for the not treated if they were to have been treated, right? So that's where things get kind of confusing, because I'm conditioning on actual treatment status, right? But these people aren't treated. That's problem number one. It's impossible to estimate something that doesn't exist in the data. So all of sort of treatment effects econometrics is about trying to figure out a way to estimate a term like that, something that we actually don't observe. So we use words like counterfactual and some of these. Which one of these is more interesting? Depends on what you care about. So the overall population average essentially tells us something like, is the policy useful from a societal perspective? It's like a cost-benefit comparison. So if the average outcome for the treated exceeds the average outcome for the untreated, then society gains. It's not a Pareto statement, but it's an average statement. Okay? So we would like to think that all the policies the government invokes have that sort of outcome. That's pretty rare. Okay? Maybe, on the other hand, we get policies that have very specific impacts on very specific subpopulations, right? And those can also be extremely useful, right? We would like to think that if they invoke something to help people, it actually works, right? So we'd be a little more, so there, an NHI is sort of a national policy, okay? So we would, I think, at least to some degree care about this measure if we try to look at the impact of NHI if it actually ever happens, okay? On the other hand, we might be interested here in whether or not supporting things like affirmative action actually lead to better outcomes in the labor market for the people it's meant to help, right? And so then we probably think more about this. Okay, so it's not that one's more interesting than the other, it's that one has a slightly more, well, they fit, they're based on the question you're trying to answer, right? Which one is more relevant, depends on what you're after. And in practice, it sometimes actually just depends on what you can do. Sometimes you can't get one or the other. It does happen. Okay, so what is an average treatment effect? There's a somewhat simple table of a population that I made up. Actually, I stole from Alberto Abadi, to be fair, because he and Josh Angers gave a lecture that was pretty cool, and I liked this slide. So basically, we've got 4 individuals in this population. Okay, it's not a sample. We're going to call this a population. 4 individuals. I observe both the treatment outcome and the non-treatment outcome. Right, so I know, I'm God, I'm Donald J. Trump, right? I know what these values are, okay? And then I've got treatment status, 1 and 0. And then I've got differences, okay? So these are simple mathematical differences, right? 6 minus 2 is 4, and so on, in case you were struggling with that. Hopefully you weren't. Okay, so how do I figure this out? Well, 4 individuals in the population, I'm going to weight them equally. And that then means that I can calculate the expected value, which is essentially the average, right? So the average here is 3.5. The average here is 1. I'm not going to take the average of this treatment status, although I could. And that gives me the expected outcome for the treated is 3.5. The expected outcome for the untreated is 1. So the gain to society in this made-up example is 2.5. And so whatever this treatment is, yes, we should do it as long as it's cheaper than 2.5, whatever these units are, right? That is somewhat different than, did I not change it? Yeah, I did. That is somewhat different than the effect of treatment on the treated, okay? So now we're going to calculate expectations based on actual treatment status. I only have 2 individuals that are treated in this population, so these 2 individuals are no longer relevant to my question, okay? It is now 6 and 4. The average of 6 and 4 is 5. 2 and 1, the average of 2 and 1 is 1.5. And so the average gain now for the treated is 3.5. Everybody see where all those numbers come from, hopefully. Okay, if you've got questions, please, let's make sure this is clear. All right, so in this example, right, those who are treated gain more than society on average. Okay, that doesn't have to happen that way, but that's also fairly common. This is a perfect world where we actually can see these outcomes, right? And it's this bit that we're making sort of assumptions about being able to see. In a less than perfect world, we're going to be missing data, especially in a cross-section. It might look like this. I observe the treatment outcome for 2 individuals. I observe the non-treatment outcome for 2 individuals, and I observe treatment status. This is probably a bad example because I'm assuming I observed the treatment outcome for somebody that wasn't treated, but this is a generic sort of statement. It's not meant to be absolute reality, okay? I've got missing information, and because I have missing information, I cannot figure out what these are. without making some assumptions, right? So back to what we do all the time as economists. We make some assumptions, and we hope that at least a couple of them are right. Okay. So this essentially is termed an identification problem. So if you've read any sort of fairly recent papers in the field, you'll see them talk about identification. This is an incredibly important issue in terms of, and it's basically what sort of assumptions are you making for the parameter that you're estimating to be the parameter of interest. Okay, so in a world where D is endogenous, we have at the very least a selection effect. I could go a step further and break the selection effect into a couple of pieces. I'm not going to do that here because it's not necessary. This is what we want to get across at this stage. Right, so the basic argument I'm going to make is that we can see in a cross-section, I can see here's a bunch of individuals that have completed matric, here's a bunch of individuals who haven't. Or here's a bunch of individuals who have access to a medical aid, here's a bunch of individuals who don't. Okay, that's what I can see in the data. All right, so if I was to calculate a simple average of, I don't know, employment or earnings for the people that had matric, and a simple average of employment or earnings for those who did not have matric, it would be this, right? And I could take the difference between those. So it's what I observe. It's the earnings for those who have completed matric, and I take an average. It's the earnings for those who have not completed matric, take an average, right? I can calculate that. That's easy. Give me a data set with a dummy variable or something I can use to create a dummy variable and some outcome variable. I can do this, right? I'm a genius, right? This is easy. Okay. The problem is that's got almost no meaning because it captures two pieces. One is it captures what you might want to know, which is what did matric do for the people who completed matric, right? And captures something else, which is this idea that there are some people that find matric a whole lot easier than others. Okay? And that's the selection effect. And sometimes that selection effect is far bigger than the actual treatment effect. So we get this biased estimate because our estimate includes two pieces and doesn't help us. We don't know what we're actually, well, we know what we're estimating. We're estimating an observed difference, but that observed difference doesn't have any actual meaning because of this. Now, mathematically, this might look kind of unusual, and I think it's worth just talking about this for a second. I am trying to figure out the average non-treatment outcome for those who are treated compared to the non-treatment outcome for those who are not treated. Okay, and to get this right-hand side, I want you to notice that I have essentially added and subtracted the same term. Okay, so I'm adding and subtracting 2 or something, right? So I haven't changed the equation any. What does that mean? Okay, I call it a selection effect, but what are we talking about? Why is it a selection effect? Well, because what we're basically arguing here is that people who get matric have different non-matric outcomes than people who do not get matric. Okay? Or people who take this even a step further, right? If we're interested in like the effect of medical care on people's health, right? People that go seek medical care seek it for a reason, right? If you've got a simple cold, you're probably not going to go see the doctor. Whereas if you're like really sick, you may go. And so there's the type of people that go and do these kinds of things differ, okay? And that's what we have to keep in mind. Now, there's lots of reasons why people won't complete matric, not all of which is related to ability, right? But these are parts of the story. Okay. So what are we trying to do? So the basic point that we're trying to make is that we can observe treated outcomes and we can observe non-treated outcomes. I'm using the word participant, non-participant, which maybe is a bit confusing, but basically I can observe those who've been treated, I can observe their outcome. Those who haven't been treated, I can't observe their treatment outcome, but I can observe their non-treatment outcome. I don't have the opposite. Right? I cannot observe the treatment outcome for somebody that wasn't treated. It just doesn't exist in the data, okay? So I need some form of conditional, exogenously, let me say this better. I need conditionally exogenous participation measure. All right, so this gets solved in a number of ways, but for now we'll talk briefly about two of them, one of which we're going to move to. So randomized controlled trials. Right, so one thing I could do is I could get a whole bunch of money from Bill and Melinda Gates, and I could try to make sure that, try to support people to get through matric, and the rest of them say, screw you, you don't get anything, okay? And I randomize those people, and then I watch them 10 years later to see what happened, okay? So I use randomization to try to get exogenous participation. So they don't go to matric because they want to, they go because the money's there, right? It's somebody's been chosen to be given to be supported, somebody has been chosen not to be, right? That's great. It's wonderful from a statistical point of view. I can make participation exogenous. So now I can just compare the difference in means. That'd be great. They don't let me do these kinds of experiments on people. Oh, you can go to school. No, not you. You know, right? They don't let me do that. So it's not easy. The ethics around randomized controlled trials is fairly complicated. So what you can do in a randomized controlled trial, in my view, is quite limited, right? And I mean, some of them are fairly interesting, to be fair. And they've learned a lot from doing these, but there's a lot of things we can't do in this fashion because it's kind of ethically wrong. So instead, and what we're going to talk about most of the rest of this session, is we're going to try to make it look like a randomized trial. And we're going to play with the data in such a way to make it look like the observed and the participants and the non-participants are the same. Okay? In a randomized controlled trial, they are the same. It's just that somebody's been chosen to participate and somebody not. Okay? So we're going to manipulate the data in a way to make it look like it's randomly assigned, this treatment status. Okay? And then we'll move forward and we'll talk about endogeneity using instruments and so on a bit later. Okay, but that requires a slightly different set of tools. Okay, so here's matching. We talked about it a little bit yesterday when Blessings talked about, maybe I should stop playing with my ear. So when Blessings was doing synthetic controls, we saw some of this idea that we're trying to create a comparable control group to California, right, where they changed the smoking law. Okay, so we used information from other states, and we talked about weights. And the idea was that we would reweight these states to make them look like California, because nothing looks like California. Right, so you have to sort of make it up in some way. Here's the principal idea. I've got a treatment status that I'm interested in. That treatment status affects the outcome. So this is the easy bit. Right? But I've got some noise, things that I don't know. Right? And again, this is like almost everything. I don't know. Yeah, I don't know most things, right? I just act like I do. So this is noise, this is error. We don't observe this kind of stuff. Certainly that's going to affect who gets treated, okay? And it's very likely to affect the outcome. Okay, so that's what this picture is trying to say. It's a simple path diagram. Right? This sort of comes in and out of fashion in econometrics. Lately, it's gotten a lot more push because of actually a computer scientist who has spent most of his life trying to argue that if we're going to get computers to think, we have to give them the ability to reason, and that means they need to understand causality. What causes this to happen, right? And so he spent a lot of time thinking through all of these kinds of things with Bayesian analysis and so on. It's actually some interesting reading. His books are interesting. His papers are flipping hard. But anyway, our problem is this, okay? Because the error term affects the treatment status and the outcome, I can't find just that bit, okay? Because I can't observe this, okay? There's a path from D to Y, but that path from D to Y is confounded by the noise in what I don't observe, okay? So the easiest thing to do, of course, as an economist is assume it away, right? And that's basically what we're going to do. This is what matching does in a nutshell. It assumes that everything I can't observe, I actually do observe. Right? Brilliant. There's a bunch of confounders that are not unobserved. Or maybe that's a bad way to say it. They are observed. These are specific variables. So I know something about somebody's age. I know something about where they grew up. I know something about their parents' education or their parents' something or else. All right? And so I can use those to try to explain as much of the noise as possible. Okay? And we're going to go a step further and essentially assume once I have used these outcomes are entirely independent of treatment status conditional on them, those outcomes, right? So basically what this statement is saying is that once I know these, I can explain this bit of the path and I can explain that bit of the path so that what I want is all that's left over, okay? It's a little bit like cheating, but it's justified. Okay. So they were making this massive assumption that once we have all of these variables that we can observe, there's nothing more that we don't know that matters, right? So it's a big assumption. Okay. In principle, economists don't love this. Right? You don't see a lot of matching papers published in top journals. You really don't. Why? To them, it's a huge assumption, right? But there are other things we don't observe, right? So you have to, when this first sort of started, it was fun and popular, and then people started ripping it apart. Okay. But it's still useful to understand. Let's talk intuitively for a second. All right, so here's some data that we had not so long ago. I now only have the Y outcome. I don't have it split by Y1 and Y0. Okay? Because I only observe the actual outcome and the actual status. Okay? So this is like a real data set, even though it's very small, but I think the point comes across. So I've got 3 different x values, 2, 1, and 0. And what I'm going to do from the point of view of matching is I'm going to try to find x's that are similar so that I can compare outcomes for those kinds of people. The key issue is I need their treatment status to be different. Okay? So here's the idea. This person was treated, right? This person over here was treated. They have an x value. This person over here was not treated. They have an x value. Maybe those x values are really close. Okay? And I'm going to basically say that since their x values are close, or basically the same, they're identical people. The only difference is that one was treated and one wasn't. And now I'm going to compare the difference across them. Okay? So we can imagine we can put the 2's together, right? There's 2 2's here and a 2 there. The 1 and 0's are probably a little problematic, right? Because you have to think a little bit about how you want to match the 1's and 0's, okay? So one of the things that often happens when you start to match, you actually lose data, okay? Here in this particular case, I'm going to make a really strong matching assumption that the x's have to be identical, okay? So I can imagine a treatment where I'm putting observations 1 and 3 together. Observation 1 is treated. Observation 3 is not treated. The difference in outcomes is 6. But the x's are the same. Or I could put 1 and 5 together, right? The x's are the same. The difference is 3. Right? So now I've got multiple results for this treatment effect. I've got 6 and I've got 3. Or I could match multiply, right? I could put multiple matches together, and then it would be something like matching 1 with 3 and 5. And take some sort of average, right? So 6 minus the average of 0 and 3, get something like 4.5. Okay? You follow the logic at least. Okay. Because if there's questions, we should clear that up. All right. So that's basically what this slide tells us. I've got a couple of options. I could put 1 and 3 together, 1 and 5 together, or I could match 2 to 1, right? Where I've got 2 untreated with 1 treated. I could do this with the average treatment on the untreated as well, but I don't want to go through that one. Okay. Okay. So, this underlying parameter of interest is basically I am trying to find some x's that once I condition on those x's, they make this treatment status independent of the outcomes. Okay, what that basically means is that this error part of the story goes away, right? So everything between D and Y tells us what's going on because I've gotten rid of all the extra noise in that picture. Okay. Because they're independent of D once I have the x's, these two statements are identical, right? So the outcome for the treated, given treatment status, should be the same as the treatment outcome for the untreated, right? Because I've made this assumption. The outcomes are independent of D once I control for the x. So I'm controlling for the x. So it doesn't matter what D I have, the outcomes are independent. So I'm just writing these two different ways and rearranging. So now the average treatment effect on the treated is some slides back. It is the treated outcome given treatment minus the untreated outcome given treatment. But through matching, I can replace the non-treated outcome for the treated with the non-treated outcome for the untreated because I've made this assumption that treatment status is independent. Right? And so that's what we were doing on the previous slide when we were doing this basic matching story, right? I was saying, okay, here's some x's that are the same, right? So I'm going to put them together and I'm going to compare their outcomes, right? So I'm assuming that the only thing differing between them is the treatment status, but they're otherwise the same people. Okay? That's what this math is trying to say. Now, this is not a particularly great way to do things. Why? Because, well, there's lots of x's, possibly. If you've ever worked with a cross-sectional data set like a StatsSA labor force survey, there's like 300, 400, 500 variables in such a survey. They're not all going to be relevant, but certainly even if you take this up to 3 or 4, that criteria gets really messy. Okay, so you don't want to match by the actual value of x. That's a bit of a pain. We need some sort of way to do this a bit more mechanically, right? And so this is a theorem that, who did the theorem? I think it's Rubin and it's a statistician and a political scientist, but now I can't remember who the political scientist is. Anyway, so basically the idea is that if I'm willing to make this assumption, right, that the outcomes are independent of the treatment status once I've conditioned on the x's, then the outcomes are certainly going to be independent of the treatment status once I condition on a function of the x's. Right? And this is sort of a basic statistical property, right? That if something is independent of a variable x, it's going to be independent of the function of x, right? And so this is not actually, I shouldn't say it, I'm not trying to imply that this is obvious, but it's not a wildly outrageous sort of extension to the idea, right? But the point is, I'm making this assumption. I am assuming that these are independent given the x's. So instead of then working with all the x's at across all of these different observations, what I'm going to do instead is work with one function of the x's. So now I basically have one number. Okay, and that's going to make my life a whole lot easier. So we call this conditional exogeneity. So I no longer have a selection problem because I have conditioned on the observed data or a function of the observed data. And basically what I've got now is, in order for me to calculate this gap, right? I mean, it's an ugly mathematical expression, but in order to calculate the difference between the treated and the untreated, which was basically what we're interested in, all I have to do is match a sample of untreated to a sample of treated individuals, and I take the difference in their outcomes. Okay? That's what this expression says. So instead of my confounders from that previous picture, I'm now replacing all of my confounders with one number, a propensity score. So I'll come back to this basic idea. If we have a randomized controlled trial, the idea is that we're randomly placing people into groups, but in principle, those groups should be fairly similar. You want people of the same age, you want people of the same illness level or income level, lots of things like that. You're going to try to make the groups look very similar, and the only difference is one group will be randomly assigned to be treated and the other one won't be. Okay? That's what goes on in an RCT. And you always see people talk about balance. How balanced are my groups? With matching, we're trying to do this the same way. We're trying to say, okay, we know they're not randomly assigned. We know that some people pursue education maybe because they find it easier, and some people don't, or many other things that we might be interested in. So what we're going to do instead, we're going to try to make them look like they are. We're going to try to make them look like they're balanced, like they're the same types of individuals. Okay, so matching looks like RCTs if you're willing to make the assumption that the treatment status becomes random once you've dealt with the covariate differences. And basically what's happening here is this is a way of thinking about reweighting the data, much like we talked about yesterday afternoon with synthetic controls. Okay. So we're going to try to estimate a matching weight, and we're going to use that weight in a weighted regression. Generalized least squares kind of thing. Okay. But there's lots of things that people have done sort of in between. So I'll talk about a few other things along the way. When does this break, by the way? Because I see people want to quit listening to me. 10, okay. Can you make it another 30 minutes? Sweet. Okay. So, hopefully this looks somewhat familiar. So we're going to define a simple dummy variable. Somebody's treated or non-treated. So 1 for treated, 0 for not. I don't have to do it that way, but it's just convenient to keep this constant. I'm going to have a vector of covariance x, and I'm always going to include an intercept. So my propensity score is going to be the probability of treatment given my x's. How would I estimate that? How do I estimate a probability model? With a logit or a probit. All right. So literally, that's what the first stage is. We're going to estimate a logit or a probit. I can use funkier probability models if I want to, but if I've got a binary treatment, right, one or zero, then probit's fine. If I've got multiple levels, then it might be a bit more complicated, and the matching process there is maybe less clear. Anyway, so basically what we're going to imagine is estimating this sort of probability model. Now, in a perfect world, you would actually know what the propensity score was, right? That's kind of the assumption here. We know the propensity, how likely it is for an individual to be treated, right? There's some sort of population value, right? That's why we don't actually call it a probability. We call it a propensity score because there's some sort of population measure out there. And we're going to estimate that population measure with a probit model or a logit model, right? And what we care about is not we don't care about the marginal effects. We don't care about the parameter estimates. What we actually care about is the prediction from the probit model or the logit model. That's what E is. This is the actual probability that comes out of the model. We basically make 3 assumptions when we do this. That one's not there, but that's okay. 2 is the one that, well, yeah, let's call it 3. Depends on sort of which book you read. Some will say 2, some will say 3. The first one is balance. Right, so this idea that we are trying to make something look like a randomized controlled trial, so we want the 2 groups to look similar. Okay? That's the balance concept. We want the treated group and the non-treated group to look very similar. So the whole point of this propensity score matching is to mitigate the observed differences in the x variables. Okay? And a couple ways to think about that, but we'll talk about them, at least some of them. The 2 big ones, well, the biggest one is this one. It's called strong ignorability. It is that, I'll read what I've written. The treatment assignment and the observed covariates are conditionally independent given the propensity score. In other words, the confounders are enough to get rid of the endogeneity. Right? That's this big assumption that underpins all of matching. Okay? And then overlap is something that's required to make sense of your results. Okay? So the overlap concept is that if I'm going to compare treated and non-treated, I want them to look similar. So in practice, what that means is I need for them to have propensity scores that are plausibly similar. Okay? And in particular, I can't have zeros and ones, right? So I can't compare somebody that is obviously treated to somebody who's obviously not treated. There has to be some level of noise. It has to be bounded away from the endpoints. Okay, that's the 0 and 1. So that's the minimal assumption of overlap. The one here that's not showing up on the screen basically says it's probably a little bit better to imagine comparing people maybe in a range of probabilities so that you're more convinced that they're really similar. Okay, so you can limit this even farther away from 0 and 1 if you need to. So from this, in particular from strong ignorability, I can make the argument that my difference in outcomes given the x's is the same as the difference in outcomes given the x's conditional on treatment status. So strong ignorability allows me to add the treatment status conditioning in this first part of the equation. And the second part of strong ignorability means that it actually is independent of the actual level of treatment. So I can take that gap as well. So I can find that difference between the two. Once I have common support, I can integrate that difference over a region of the data. And then this is just some measure, right? So in practice, we don't do integrals. Okay, so if you don't like integrals, that's okay. But in practice, what we do is there are two measures that we can estimate. One is an average treatment on the treated, and the other is an average treatment effect of sort of the population. And if we're going to do the average treatment effect on the population, we actually do this process slightly differently than if we're just doing an average treatment on the treated. Same sort of story here. More basic argument that with strong ignorability, I can do this conditioning. This one doesn't really do much here. And it's pretty much the same equation from the previous slide. The real difference is really over here in that I'm basically integrating over a conditional distribution instead of a full distribution, right? That's the main difference between the two equations. And now we're basically matching in one direction. All right, so what does that mean? So I'll talk hopefully when we do practical kind of things. So if we want to know what the effective treatment is, the basic idea is to take treated people and match them to untreated people. On the other hand, if we wanted to know what the effect of not being treated was, we would take non-treated people and match them to treated people. If we want to know the overall average, we would do both. We would calculate essentially an average treatment on the untreated as well as an average treatment effect on the treated, and we would basically take an average of those two, and that would give us the overall average in the society. That's what I mean by one direction versus two. Okay. So here's the general way to estimate it. It's always cool in terms of letters. But basically all it says is we're taking the average difference between a treated outcome and whatever you've matched that treated outcome to. That's what the J bracket I. So this J bracket I is that you've assumed to have matched one individual, J, to I, right? The treated individual. So this one makes some sense. Here it gets a little bit more complicated because now we're matching more than one individual. So if you might match 2 or 3 or 4 individuals and use those 4 that you've matched to get an average match, if you will. Okay? So basically it's the same idea. I'm taking the difference between the matched person and the actual person, And here I'm taking the difference between the average matched people and the person. There's a whole side literature on what's the appropriate number of matches, and the answer is 4. Don't bother to go beyond 4. And the reason for that is that all you get when you start matching a little bit more is you get a decrease in the variance of the estimator, but that improvement stops after 4. So don't bother to match to 8 people. Nobody will care. But I think matching to 1 or 2 is perfectly reasonable. But you see words like this, 1 to 1 and 1 to m. You also see things like kernel matching and a few other things. Those are details related to this. Kernel matching, just for a brief description, I don't have it anywhere in my slides, but kernel matching basically says let's find all the matches that are within a small bandwidth of the actual individual. And what means, sorry, there might be in some cases more than 1, in some cases less than more than 2, and so on. So the number of matches actually isn't constant all the time in a kernel match, because of the way the weights of the kernel estimator work. But it's really not that big a deal. Here's an even cooler equation, right? And it's really just because it's cool. It says, a couple of moments ago I said with one we match one way, right? And with the other we match 2 ways, right? So now you see the number 2 here. Basically what we're doing in the sort of overall average treatment effect is we're matching the treated to, so D changes, somebody's treated or somebody isn't treated. So if somebody is treated, this is 2 minus 1 or 1. If someone isn't treated, this is -1, right? And we're matching the sort of treated to their match, or the untreated to their match, right? And with the negative sign, the sign changes, right? And it all adds up, okay? So don't worry about the exact detail of that, but this is a way of writing down the average treatment effect to allow for matches in basically both directions, okay? All right, so here are our assumptions again. We need balance. We need the covariates to be similar after matching.
I didn't catch that.
We need the covariates to be similar after matching. How do we typically do that? Well, the most common ways to do this is to think about means, right? So t-tests or f-tests. There's a slightly different side of statistics that looks at broader distributional tests like Kolmogorov-Smirnov tests or entropy tests. They can also be used if you have like continuous variables, say income. And they're actually slightly better things to use than just t-tests or f-tests, because if you've got continuous data, 2 variables might have the same mean, but they might be distributed wildly differently. Okay, and so there's some logic to being a little bit more detailed on your balance test there. Strong ignorability is untestable unless you have an instrument. We'll talk about instruments later. So strong ignorability is an assumption. That's it. There's no way around it. Okay. Overlap isn't really a test. It's a requirement. And so this is easy to impose on the data. You just say, oh, there's clearly no overlap in this part of the distribution. Let's throw away these observations. So fairly easy to do. Yeah. So it's a standard approach is to do covariate by covariate t-test. So let's look at, I've got a couple of dummy variables. Let's see if they're on average the same. I've got a couple of continuous variables. Let's see if they are the same on average. Right, but the reality is we're conducting tests across a lot of things at once. So there's this other side of statistical literature which says, well, if you're going to conduct multiple tests, you should use a test that is designed to deal with multiple tests. All right, so this is where F tests come from. Sorry, this is spelled wrong. Bonferroni has suggested a fairly straightforward correction. So you can do T tests with a Bonferroni correction, which basically says if you've got, say, 5 T tests that you want to do, and you're using an alpha level of, say, 0.05, then this just says take the alpha level and divide it by the number of tests you're doing. Okay, so that's the simplest t-test kind of correction you could do. But f-tests are not a bad idea. You've got sort of six things you're testing at the same time. Let's do this all as an f-test, which essentially implies that you're going to run some sort of simple regression and test whether or not all of the parameters are 0, right? I think most people have seen t-tests, right? But there's your classic t-distribution. And let me just show you briefly what happens in a Kolmogorov-Smirnov test, which is basically trying to find the largest difference between two distributions, right? So you imagine a distribution function, how the data goes, and it tries to find which one's the largest, where the difference between the two distributions is the largest. And then it asks whether or not that difference is so large that we should believe that those distributions are different, right? So it's not a mean test, it's an actual test of the underlying distribution of the overall, of the total data, right? And so here's the sort of calculations you do, right, depending on what alpha level you have. And then N and M are the size of the two samples, right? So it's not a particularly complicated test to do. And again, most software will do a KS test for you. It's not very hard. But it's based on the empirical cumulative distribution function. Okay. Yeah, let's do this. So it is possible to do matching with other things besides the propensity score. This one should look fairly similar to what Blessings was talking about yesterday. What's missing is the square root here. Right? But basically it's the gap between the treated and the untreated x's, right? Weighted by some sort of variance matrix, covariance matrix of the data. Okay, so to do this, we kind of randomly order the data. We measure the distance for the first treated observation against all the other untreated, and we find the one that's the closest. All right, so this is I don't know if it's more complicated to do than others from a sort of pure programming perspective, but you imagine you find a match that's the closest based on this metric, and then you find another match based on this metric, and so you keep going. Sorry, this didn't show up as a series of bullet points. So the x's are the covariates, C is the covariance matrix for the x variables, and if you want, there's nothing stopping you from actually estimating a propensity score and putting that in the x's. Okay. Nearest neighbor. Now here's this sort of a slightly different way of saying what we said a moment ago. The nearest neighbor is, now if we think about just looking at propensity scores for the treated and the untreated, remember we're estimating the probability that treatment is given, and we're using the whole sample of treated and untreated individuals. So we're taking all of the treated individuals, no, not the untreated, all the treated individuals. This is bad. And we're trying to find the, oh, no. Okay, sorry. I know what I'm saying. We're taking all the untreated and we're trying to find the untreated that are the closest match to the treated based on the propensity score. So we're trying to find the closest score. Okay. You can match more than one. If you've got small data sets, you might worry that these matches are maybe too far. Okay. So if you're worried that the matches might be too far, you could limit how large the match distance is allowed to be through a caliper, all right, which is just a fancy way of saying you're constraining the size of the gap. And the most common one to use is 1/4 of the standard deviation of the propensity scores. All right, there's a literature suggesting that that's a useful approach. You can do Mahalanobis matching with a caliper. Right, so now these just get, cute ways to revise the different types of matching estimators, right? So we've got Mahalanobis matching, sort of limiting the actual propensity scores. So we say, okay, well, here's a band of propensity scores. Let's do some matching in this particular band. And that's kind of what this is arguing we could do. Defining what that actual eta value should be is maybe not obvious. But yeah, these are sort of different ways of redoing the matching. And then finally, another political scientist, Sikon, has sort of arguing that we should think about an optimal balancing metric. So here the argument is that, look, when we're doing matching, we're trying to get balance in the right-hand side. So we've got underlying t-tests, and we've got underlying Kolmogorov-Smirnov tests, and so on. And so this genetic matching idea is to say, okay, well, let's actually do our matching to get balance optimized so that the t-tests essentially are all insignificant. The KS tests are all insignificant, right? So you're trying to essentially maximize or minimize the p-values from these different tests. And it works out to be, again, some sort of relatively complicated distance metric, right? We're looking for the difference between treated and untreated, weighted by some things related to the different kinds of tests and a few other kinds of things, right? So this is just a way of trying to do the matching that forces balance in the data. It's a occasionally very long metric to run. Okay. Let me take a look quickly. Yeah, time doesn't quite work. Just debating where I want to stop this. Okay. All right. So once you have matches, it's fairly easy to calculate the treatment effect. Basically, we're trying to find, so here we're conditioning on the treatment, on the propensity score. So we're just saying, okay, well, let's match based on the propensity score. So I'm trying to think about, all right, so I'm going to try to say this clearly. Although we're talking about matching on propensity scores, we're saying, okay, well, here's a propensity score, say of 0.1, somebody that looks like they're untreated. And here's an untreated person with a propensity score of 0.1, and we're matching them, right? We're kind of putting them together and we're comparing the difference. But that's not in practice how this gets done. What gets done instead is we've got overlap. We've got some treated individuals and some untreated individuals with similar propensity scores. Okay? And all we're doing is we're calculating the difference between the outcomes for those individuals that are kept. All right, so we might throw out observations because their propensity scores don't match, aren't appropriate. Okay? And basically all we're doing is taking the average between the treated and the untreated. Right? Very easy to do. In practice, I have a match, but I don't really use it. Okay. But I can specifically match. I don't really have to. It might make more sense to match within stratum, right? I'm using the word match implicitly. So now I say, well, I think I'd like to compare high propensity score people to high propensity score people and low propensity score people to low propensity score people. So that's what I mean by strata of the data. And so we're basically doing the same thing. And that just means that I'm going to take the average difference within strata. Okay. And then I might weight those to get an overall average if I want to. Okay. So these are all ways that I might think about matching estimators. But here's the biggest problem with matching. And another reason why almost nobody did it. Because in principle we're matching, standard errors are really painful. Okay? So if you think about standard econometrics, we might say something like the data is fixed in repeated samples. Does that sound familiar? It's one of the assumptions we might make about the x's, right? And that underlying assumption is what allows us to essentially calculate fairly simplistic standard errors for regression estimates. Now, in more general theory, we'll use asymptotic properties, and we won't make the assumption that it's fixed in repeated samples. We'll say things like it's finite and a few other things, and the asymptotics give us really nice behavior. Okay. But with matching, it's not fixed in repeated samples. If I take a random sample of my data and I match, and then do it again, take a different random sample of my data and match, I will very likely get different matches. That's what I mean by not repeatable. And because I get different matches when I go through it again, there's no way to create finite properties or asymptotic properties of the estimating standard errors, because I don't know what the underlying behavior of the data is. So I can calculate the matches really easily. Okay. I can calculate the means really easily. But up until 2016, nobody had any idea what the standard error was. Nobody. Right? So the 2006 paper by Abadi and Embens essentially said, you can't do this. Don't do it. Don't bootstrap. It's a horrible idea. It's garbage. You don't know what you're getting. I forget what the 2008 paper says, but the 2016 paper says, oh, by the way, here's the actual underlying standard error for a matching estimator. And what's really interesting about this, so, sorry, the 2000, that's what it is. 2006 paper, sorry, back up. We're actually estimating this propensity score, right? So we've got the thing that we're using to match with is estimated. So it's on its own is noisy, okay? And so there's this side literature, again, in econometrics that says, look, if you're estimating something in your model and you're using that in your model, right? So you estimate something first and then you use it for your model, then your underlying standard errors are affected by the fact that you've got noise that you're ignoring because your estimate is noisy. Okay, so you're supposed to include that, and the usual solution to that actually is bootstrapping. Okay? And memory serves me correctly, the 2006 paper says no, bootstrapping doesn't work because we can't define what the noise is. Okay? So, for the most part, when we're doing this in sort of standard econometric models, the fix, right, this bootstrapping fix to deal with the additional noise means that at the end of the day, the underlying standard errors are all bigger, right, because we have to add the noise. Right? The 2016 paper says, no, in fact, the additional noise that you create from estimating the propensity score actually reduces the underlying standard error. It's like the only case that I know of where this is true. Okay, you're still not allowed to bootstrap, okay, but it gives you a fairly messy way to calculate the standard errors in a matching regression model. But because getting these standard errors is such a pain, nobody actually does matching in this way. So I've spent an hour and a bit telling you about how to do matching, and nobody does it this way. Okay? But intuitively, it's useful to understand the idea, right? That you're trying to take something that is different, well, two people that are probably different, one's treated and one's not, and you're trying to make them look as similar as possible, right? That's the concept behind matching, okay? How people actually estimate this is this way. These are weights. So I've got an outcome here. I've got the treatment status here. I've got the estimated propensity score here, here, and 1 minus the estimated propensity score here. Same thing over there. Plus I've got an underlying probability that D is equal to 1, which you get in the data as well, right? So the sample is 400 people, 250 are treated and 150 aren't. Right? You use that as your probability of treatment in the overall sample, okay? So this is a simple weighting measure. You calculate the weighted mean in the data based on these estimated values, and you just create this weight. D minus E divided by E times 1 minus E. So you estimate the propensity score, you create these weights. These weights are noisy because they're estimated, but you can bootstrap these because you're not matching anymore, you're just weighting the data. So this is entirely allowed from a bootstrap perspective, whereas matching is not. So this is how people actually do the estimation. It's basically weighted least squares, but it's bootstrapped. You repeat the process to get the standard error of the estimate. Okay. To see that these are actually correct, let me pause there actually. All right, so we'll come back to this because it's 10 o'clock according to Mickey.